Cape Canaveral Space Center. Just seconds after liftoff, a massive rocket suddenly explodes high in the sky. Millions of people watch the disaster unfold live on television. Later, investigators discovered that the cause was nothing more than a tiny rubber seal worth only a few dollars. The freezing temperatures had prevented it from functioning as intended, and that single failure was enough to destroy one of the most sophisticated machines ever built by humanity. The tragedy forced engineers to confront a question that had challenged them for decades. At first glance, a rocket seems surprisingly simple. A giant fuel tank, an engine at the bottom, and that's about it. In reality, nothing could be further from the truth. Every single component must perform flawlessly because even the smallest mistake can trigger a catastrophic failure within the first minutes of flight. So how are rockets really built? And is it actually true that nearly 90% of a rocket's mass is nothing but fuel? Imagine building a gigantic truck just to deliver one small box of chocolates. To carry that tiny package, the truck would need to be the size of a skyscraper and weigh hundreds of tons.
That isn't an engineer's wild fantasy. It's the harsh reality of spaceflight, dictated by one fundamental law of physics that no modern technology can overcome. The great scientist Konstantin Tsiolkovsky developed an equation that became both the greatest blessing and the greatest curse for rocket engineers around the world. His formula describes the mathematical relationship between a rocket's mass, the speed at which exhaust gases leave the engine, and the vehicle's final velocity. The problem is brutally simple. Moving a heavy metal tank filled with fuel requires more fuel. But that additional fuel also has weight, which means even more fuel is needed just to carry it. This endless cycle forces engineers into incredible compromises, reducing the useful payload to a mere 2 or 3% of the rocket's total launch mass. To outsmart this unforgiving law of physics, engineers came up with a brilliant solution. They divided rockets into multiple stages.
Once a massive fuel tank is empty, it is immediately discarded during flight, allowing the rocket to shed enormous amounts of dead weight in an instant. The greatest expression of this concept during the 20th century was the legendary 3-stage Saturn V rocket, created under the leadership of the brilliant engineer Wernher von Braun during the 1960s for America's Apollo moon program. Standing 111 meters tall, this enormous machine weighed nearly 3,000 tons. Of that total, around 2,700 tons consisted entirely of fuel and liquid oxidizer. The gigantic first-stage tanks carried more than 2 million liters of kerosene and liquid oxygen. That entire supply was consumed in just 150 seconds by 5 colossal engines, lifting the rocket only 67 kilometers above Earth. That tremendous firestorm at launch had one purpose alone. It existed simply to accelerate a spacecraft weighing only 45 tons and send it toward the moon, demonstrating just how unforgiving the laws of space really are. Carrying such enormous amounts of fuel demanded tanks of incredible size.
But if those tanks were built with thick, heavy walls, the rocket would never leave the launch pad. Every 100 grams saved from the structure translated into precious extra velocity once the vehicle reached orbit. That's why engineers began designing fuel tanks whose walls are closer in thickness to an ordinary aluminum beverage can than to the armor of a military vehicle. If you step on an empty soda can, it instantly collapses beneath your weight. But if the can is sealed and filled with pressurized gas, it can easily support the weight of an adult. Modern rockets rely on exactly the same principle. In some places, the metal walls of their fuel tanks are no thicker than a common kitchen knife. Engineers use what is known as a load-bearing shell structure. Instead of depending on thick internal beams or heavy reinforcing frames, the rocket gains much of its strength from internal pressure. Inside every tank, helium gas or evaporating nitrogen continuously presses outward against the thin walls, keeping the metal stretched and rigid. This allows the tanks to be built from extremely lightweight aluminum-lithium alloys that are only 3 to 4 millimeters thick, even though the rocket itself may measure 9 or even 10 meters in diameter.
Welding these enormous metal sheets is an extraordinary engineering challenge. Every weld is carefully examined using ultrasound and X-ray imaging to detect even the tiniest microscopic cracks. Yet this remarkable weight-saving design comes with a frightening downside. If the pressure inside the tanks drops even slightly, the rocket can instantly lose its structural strength. Without that internal support, the entire vehicle may collapse beneath the weight of its own upper sections, crumpling into a twisted pile of metal. A dramatic demonstration of this danger occurred in 1960 during an incident involving an American Atlas rocket sitting on its launch pad without fuel. Because of a malfunction in the tank pressurization system, the internal pressure suddenly fell below the critical level needed to keep the structure rigid. Engineers watched in disbelief as the towering steel cylinder slowly developed deep wrinkles across its surface. Within moments, it lost stability and folded in half under its own weight, collapsing into a heap of scrap metal. That incident permanently proved one essential lesson. A rocket can maintain its shape only while the delicate balance of internal pressure is preserved. But maintaining that fragile balance inside an incredibly thin structure is only half the battle. The real nightmare begins when substances with radically different temperatures are brought together inside the same rocket. Separated by only a thin sheet of metal, one side contains the freezing cold of liquid oxygen, while the other is exposed to the roaring inferno of combustion. Keeping these two extremes operating safely inside one engine transforms a modern liquid-fueled rocket into one of the hottest and most demanding thermal environments ever created. Inside the combustion chamber, temperatures exceed 3,000 degrees Celsius. That is significantly hotter than the melting point of virtually every metal alloy known to humanity. Without protection, the engine would melt within seconds of ignition. To prevent that from happening, engineers use a brilliant technique known as regenerative cooling. Instead of treating the icy fuel as something that simply burns, they turn it into the engine's cooling system. Before entering the combustion chamber, liquid kerosene or hydrogen is forced under enormous pressure through thousands of microscopic channels built directly into the engine walls.
As the fuel flows through these tiny passages, it absorbs heat from the glowing metal, cooling the chamber while warming the fuel itself. That heated fuel then enters the combustion chamber more efficiently, improving engine performance at the same time. By the late 1960s, Soviet engineers under the leadership of Nikolai Kuznetsov encountered the full complexity of this challenge while developing the powerful NK series engines for the Soviet lunar rocket program. They were forced to create specialized copper-chromium alloys with exceptional thermal conductivity and coat the combustion chamber with an ultra-thin ceramic layer to prevent the metal from burning away when exposed to superheated oxygen. Even the slightest defect in that protective coating or a tiny particle blocking one of the cooling channels could cause the chamber wall to burn through in fractions of a second, triggering a massive explosion during testing. Every engine test became a dangerous balancing act, where an incredibly thin metal barrier stood between controlled power and total destruction.
But even the most advanced heat shields and the strongest metal alloys become completely useless if enormous volumes of supercooled fuel cannot reach the combustion chamber at incredible speed. To push nearly a ton of propellant through tiny injector nozzles every second, the pressure inside the fuel tanks alone is nowhere near enough. You need a pump powerful enough to drain an Olympic-sized swimming pool in moments. And this is where an invisible but merciless enemy is born inside the engine, one capable of turning even the toughest titanium alloy into something that resembles Swiss cheese within milliseconds. Rocket turbopumps spin at tens of thousands of revolutions per minute.
At those extreme speeds, they encounter a destructive phenomenon known as cavitation. The impeller blades rotate so rapidly that the pressure around them falls below a critical level, causing the liquid fuel to boil despite its extremely low temperature. This creates millions of microscopic vapor bubbles.
As those bubbles move into regions of higher pressure, they collapse almost instantly, at nearly the speed of sound. Each collapsing bubble generates a microscopic yet incredibly powerful hydraulic shockwave. The pressure can reach thousands of atmospheres. These countless micro-explosions relentlessly bombard the metal surfaces of the pump blades, tearing away tiny fragments of material and slowly destroying the metal's crystal structure. During the 1980s, Soviet engineers led by Valentin Glushko faced the full force of this problem while developing the RD-170, one of the most powerful liquid-fueled rocket engines ever built for the Inertia-Buran space program. During the earliest tests, prototype engines exploded one after another within the first few seconds of operation because severe cavitation literally ate away the turbopump impellers, reducing them to fragments almost instantly. The engineering team spent years solving the problem. They carried out hundreds of advanced computer simulations, redesigned the blade geometry down to fractions of a millimeter, introduced specially rounded blade profiles, and improved the tank pressurization system to completely stabilize the violent flow of liquid propellant. Developing this single component required years of work by some of the country's finest engineers, proving that controlling high-speed liquid flow is among the most difficult engineering challenges ever faced by humanity. Once this enormous stream of energy finally launches the rocket skyward, another challenge immediately appears. The massive vehicle begins experiencing vibrations so intense that even the slightest error in its control system can instantly cause it to lose stability. A rocket racing through the dense lower atmosphere at tremendous speed is incredibly sensitive to the smallest tilt or unexpected gust of wind.
Sometimes, installing a single orientation sensor upside down is enough to make the rocket destroy itself. Every spacecraft carries highly accurate gyroscopes and angular rate sensors that function much like the human inner ear. They constantly tell the onboard computer exactly how the rocket is tilting and how the engines must be adjusted to keep it perfectly aligned. But if the computer receives false information about the vehicle's orientation, it starts correcting a problem that doesn't actually exist. Instead of stabilizing the rocket, it commands increasingly extreme maneuvers until aerodynamic forces literally tear the vehicle apart. That exact mistake caused one of the most dramatic launch failures of the 21st century. In July 2013, a Proton M rocket lifted off from the Baikonur Cosmodrome. Only seconds after launch, the rocket suddenly drifted off course. It began swaying violently from side to side before completely flipping over in midair, catching fire and crashing to the ground just a few kilometers from the launch pad in a massive explosion.
The investigation stunned the aerospace community. During assembly, 3 of the rocket's 6 orientation sensors had been installed upside down. To force them into place, the technician had applied significant physical force, effectively hammering them into their mounts, while ignoring the alignment markings and mechanical guides specifically designed to prevent incorrect installation. As a result, the onboard computer believed the rocket was falling sideways. It immediately attempted to correct the imaginary tilt. Ironically, those very corrections drove the rocket directly into the ground, turning a project worth hundreds of millions of dollars into wreckage. Yet, even when every sensor is installed perfectly, a rocket still requires extraordinary control precision to survive the unpredictable winds encountered throughout its climb into space. Imagine trying to balance a massive steel pole while it races forward faster than the speed of sound. You have only tiny, carefully timed movements to keep it upright. At high altitudes, where the atmosphere becomes extremely thin, traditional wings and control surfaces become.
Rather than turning the airflow around the rocket,
Engineers simply tilt the engine itself, changing the direction of the exhaust plume. It's similar to balancing a broomstick on the tip of your finger. When the broom begins leaning to one side, you quickly move your hand beneath it to restore balance. Powerful hydraulic actuators, operating under pressures of hundreds of atmospheres, must tilt the roaring engines by tiny fractions of a degree in response to commands from the flight computer. All of this happens while resisting the tremendous force generated by the engines themselves. In 2010, SpaceX confronted this exact challenge during the early development of the Falcon 9 program. The company needed to prove not only that it could launch a massive first stage, but that it could also guide that stage safely back to Earth for reuse. To accomplish this, engineers combined multiple steering technologies. The engines could swivel during powered flight. Deployable grid fins acted as aerodynamic control surfaces during atmospheric descent, and small cold gas thrusters rotated the stage while it traveled through the vacuum of space.
As the booster re-entered the atmosphere, the grid fins endured tremendous heating and crushing aerodynamic forces, operating at the very limits of what their materials could withstand. Even the slightest delay in any of these control systems would have turned the returning booster into an uncontrollable spinning cylinder, destined for destruction. That extraordinary balancing act is coordinated by the rocket's digital brain. Yet during ascent, that computer faces an invisible threat unlike any mechanical failure. The danger comes directly from space itself.
As the rocket climbs to altitudes of tens of kilometers, Earth's protective atmosphere becomes thinner and thinner. With less shielding overhead, the rocket's electronic systems are exposed to relentless cosmic radiation. At that point, even the smallest software error, or a single bit of digital information flipped by a high-energy particle, can instantly transform a flawless launch into a catastrophic failure. The onboard flight computer performs millions of calculations every second. It constantly updates the rocket's trajectory, adjusts the engines, regulates fuel flow, and keeps the vehicle perfectly balanced. If a charged cosmic particle strikes one of the processor's transistors, it can change a binary 0 into a 1, or 1 into a 0. That tiny change may seem insignificant, but it can produce a completely irrational command. Imagine the computer suddenly ordering every engine nozzle to swing fully to one side. A mistake measured in fractions of a second could destroy an entire mission. A software failure of this kind doomed Europe's newest launch vehicle during its maiden flight in June 1996.
Just 37 seconds after liftoff, the rocket's guidance computer suddenly shut down. Moments later, the backup computer failed as well. Without valid guidance data, the flight control system commanded the engine nozzles to deflect to their maximum angle. The massive vehicle immediately veered off course. Within seconds, it encountered aerodynamic forces far beyond its structural limits. The rocket broke apart in midair, and the onboard self-destruct system activated automatically. When investigators examined the wreckage, they discovered something astonishing. The disaster had been caused by a single line of software. The guidance computer attempted to convert the rocket's horizontal velocity from a 64-bit floating point value into a much smaller 16-bit integer. The actual speed had exceeded the range that the older software could handle. That section of code had been reused from an earlier generation of rockets, where such high values were never expected. The conversion triggered an overflow error. The primary computer crashed immediately. The backup computer, running the exact same software, encountered the identical failure only moments later. Instead of providing redundancy, it repeated the same fatal mistake. The accident forced aerospace engineers to completely rethink how mission-critical software should be designed.
Learning from decades of electronic failures, modern engineers pushed rocket technology even further. Their computers no longer simply guide payloads into orbit. They now perform maneuvers that once seemed physically impossible. One of the most remarkable examples is landing a massive rocket booster back on Earth. Imagine dropping a skyscraper-sized metal cylinder from space at thousands of kilometers per hour. then expecting it to land upright on a platform floating in the middle of the ocean. It's like throwing a brick off a mountain and expecting it to land perfectly balanced on its narrow edge. There is almost no room for error. A delay of even a fraction of a second in engine ignition, or a slight mistake in the vehicle's angle, is enough to reduce a multi-million-dollar spacecraft to twisted metal. To accomplish the landing, engineers perform an incredibly difficult maneuver known as the suicide burn. The booster falls tail first at tremendous speed. Instead of slowing down gradually, it waits until the very last possible moment before reigniting its engines. The engines are designed to lift hundreds of tons during launch. By the time the booster returns, however, most of its fuel has already been burned away. The stage is now much lighter.
Its engines are far too powerful to hover gently above the landing pad. Instead, they must reduce the vehicle's downward speed to exactly 0 at the precise instant the landing legs touch the surface. Even a tiny timing error means failure. During 2020 and 2021, SpaceX carried out a series of dramatic tests in Texas with its Starship prototypes to master this incredibly complex maneuver. Vehicles such as SN8 and SN9 successfully climbed to an altitude of roughly 10 kilometers. After shutting down their engines, they descended horizontally, using 4 large aerodynamic flaps to control their fall. Everything worked almost perfectly until the final moments. Just before touchdown, the prototypes attempted to flip from a horizontal position back to vertical. At that critical moment, fuel pressure dropped because powerful centrifugal forces pushed the remaining propellant away from the fuel intake lines inside the tanks. Without sufficient pressure, the engines failed to produce the thrust needed for a safe landing. The vehicle slammed into the concrete at high speed and exploded